Alright, so in this video we're going to be doing the May 23 paper 2s for analysis and approaches. This is Timezone 1, higher level. So this is going to be a calculator paper, so have your graphing display calculators ready. So let's begin with number 1. We have 3 cities labeled J, D, and L, and we have this triangle, and we're given some distances and bearing measurements. So angle JLD is 25 degrees, and it says the bearing of D from J is 34 degrees. So from J, the north would be 0 degrees bearing. So 034 means that this angle is going to be 34 degrees. Right? And taking L to be directly east of J, we know that this total thing is going to be like 90 degrees, right? So Lucknow or Luno lies 500 kilometers to the east of Jaipur. So we know this whole thing is 90 degrees. So this would be then 56 degrees. So in order to find angle JDL, we would just say in this triangle, JDL, right, the internal angle should add up to 180 degrees. So JDL plus 56 degrees plus 25 degrees. That should be 180 degrees. So if you calculate what JDL should be, we should get 180 minus 56 minus 25. So that should be 99 degrees. And if you want to find the distance between L and D, city L and D, we want to find the length LD. We're given a bunch of angles here, and we want to use a sine rule, right? So it's especially important since we know this side length and the angle, and these are directly across one another. So we have 500 over sine 99 degrees, and we can say that this ratio is true for all other angles, right? So if we have, say, side length JD, that would be equivalent with sine 25 degrees. So we could have JD over sine 25 degrees. But in our problem, we're more interested in LD. So we'd write length LD over sine 56 degrees. So we can just solve for the length LD here. So on our calculators, we would get 500 times sine 56 degrees divided by sine 99 degrees. And we want to make sure that we're dealing with degrees. So this gives us 419.7 kilometers. Or we can round this to 420 kilometers. So a simple triangle problem where you need to use a sine rule and be aware of relationships where the total angles sum up to 180 degrees. Okay? And you also want to know that bearings, you also want to be familiar with the bearing notation for angles. Okay, so number 1 was easy. Number 2 is a question on composite functions. So for this one, you just need to know how these functions work, and you just need to be a bit familiar with your graphing calculator, like setting the axes and inputting the correct equation. So this should be an easy 5-pointer. So if you have the function f of g of x, right, we're basically putting in tangent x where x should be for f. So instead of 2x, we have 2 times tangent x. And instead of x cubed, we have tangent cube x minus. Okay, and if you put this in the calculator right away, we would first change this degrees mode to radians. And we can set our windows to go from like -1 to 1 based on what's given. And our y's would go from 2 to -2. So we get our window set up, and then we enter in our equation. We have 2 times tangent x minus tangent x cubed. So we get a graph that fits in here. It says label any local maximum or minimum point. So we can do second trace minimum. So the left bound, let's say, is like -1. Right bound, we'll say, is 0. That gives us a negative point. So it's negative 0.685 and negative 1.09 if you do the sig figs. So we'd have the point around here. And this seems like an odd function, right? So if you find the maximum point, we're going to get a similar mirror image. So we're going to get 0.685. and then 1.09. Okay, so this is what you get here. So we're going to label this as 0.685, 1.09, negative 0.685, and negative 1.09. Okay, and then we pass through the origin, and our x-intercepts are beneath or between -1 and 1. So this is what we're going to get. So we want to make sure that we pass through these local mins and maxes, and we have our x-intercepts that we don't necessarily have to label. Okay, so as long as you have this relative scale correct and you have the correct labels for local mix and local min and max, you should be fine. Okay. Number 3, we have a linear regression problem. So all you have to do, you got to be speedy with your hands. You got to take your fingers and put in the lists for L1 and L2 in your calculator. So you just go to stats and you can do like edit lists, because we're probably going to be given a data set where we need to enter this into our spreadsheets and find the linear regression model. Right? And then we might have to just plug in a few values to test what the question is asking. Okay? So it's a pretty simple problem, but you just need to be familiar you're using the correct features on your calculator. So it says the number of children in a park that is affected by temperature, right? So whatever the temperature is, that's going to give a prediction on how many children there are, right? So if we have a temperature of 25 degrees Celsius, that means the children will be found by this quadratic formula, right? So y is going to be negative 0.6 times 25 squared plus 23 times 25 plus 110, right? So that's all we got to plug in. And notice the negative in front of the t squared. That probably means that as temperature gets higher, the number of children out in the park will probably decrease, right? Because if it's too hot, people aren't as active. Right? But then there's also a term where we have like 23 times t. So maybe for the lower value temperatures, as it gets warmer, there's more children. But when there's very high temperatures, then the people will kind of like drop. So I'm guessing the graph would look something like this: the temperature versus children, right? So there's going to be a Goldilocks temperature where there's like just the right number of children, or the maximum number of children. But anyways, if we evaluate this expression, we're going to get 310. So we're going to get 310 children if the temperature is 25 degrees Celsius. And now, based on the number of children, y, we want to get our x, right? So usually we have y equals ax plus b or mx plus b, but in this case, it's just a switch in variable name. So we're going to get x is equal to a times y plus b. So the a will be like how many ice creams will be sold for each additional children. B would be how many ice creams would be sold if there is no children, right, in the park. So for this one, you have to put in these lists. So you can go to stats, edit, and you can put in the number of children as our independent variable. So that's going to be 81. So we have 81, 175, 202, 346, and 360. And then L2 is going to be 15, 27, 23, 35, and 46. Right, so you can do math. So you can go to stats, calculate, stats, calculate linear regression. And we're going to put in L1 and L2 into our model. So that's going to give you x is 0.0935y plus 7.43. Okay, so if there's 81 children, then I guess you would put y equals 81, and that should give you x, which is like the number of ice cream sold. So it's not going to be exactly matching to the actual numbers, but this should give you a reasonable prediction. Okay. Next, if you want to use this to find the number of ice creams sold when there's 25 degrees Celsius, we would use x equals 0.0935 times y plus 7.43. And when t temperature was 25, we found earlier that there's 310 children. So we just put in this value into y. So x would be 0.0935 times 310 plus 7.43. So that should give you, like, in decimals, 36.415 or 36.4 ice creams. Right. So the vendor can predict around 36.4 ice creams to be sold at this temperature. Next, let's do a normal distribution problem. So a company is manufacturing metal tubes for bicycle frames, and the diameters, capital D, are normally distributed with a mean of 32 and standard deviation of sigma. So we don't know the standard deviation, so chances are you're going to use the Z distribution, which is a normal distribution with mean 0, standard deviation 1. So keep that in mind. And it says the interquartile range is 0.28. So let's just draw the distribution of D, the diameters, and fill in what we know. So it said that the mean is 32 and the interquartile range is 0.28. So since the normal distribution is symmetric, we know we can go up by 0.14. So we would have 32.14. And then we'd go down by 0.14 as 31.86. So these would be the two quartiles. So there'd be 25% of all values on either tail. Okay, so here we have the IQR, which is indeed 0.28, right? 0.14 to the right, 0.14 to the left. Next, we want to say if you were to take the area between here, it's going to be like 50%, right? So if you were to do norm CDF with the mean of 32, the standard deviation of sigma unknown, and Q1 and Q3, so Q1 is 31.86, Q3 is 32.14, that should give us 50%. But the problem is that in normal CDF, we need to know both the mean and sigma, the standard deviation. So if you don't know that, we'll have to use another method. So recall that standard normal distribution from earlier, right? If you have mean 0, sigma 1, what would this have to be, right? So we could draw like a standard normal deviation right below. So if the mean was 0 and standard deviation is 1, then we can find the boundaries, the z-scores for here and here. So we'll call this like z1 and z2. So if the area under the curve is like 25%, we could go to inverse norm. So we go to inverse norm, 0.25 is the area, the mean is 0, the standard deviation is 1, right? Then that gives us the z1 value, which is negative 0.674. Okay. And since this is symmetric, z2 would be 0.674. So you could just do inverse norm. What if the area to the left tail is 0.75, right? So the z-scores of, say, negative 0.674, they correspond to 31.86. So you just use this formula. Maybe we'll write this as 31.86 minus 32 over sigma. That's going to be negative 0.674, right? Because we're going to use a formula for z-score. The z-score is found by taking the x value, subtracting the mean, dividing by the standard deviation. So if we solve for sigma this way, we would get negative 0.14 divided by negative 0.674, so it would be 0.207 or around 0.208. Okay, so the value of sigma is going to be 208 millimeters. Okay, so that's going to be our answer. Millimeters. All right, so number 5, we have binomial theorem and combinatorics. So we know the binomial expansion formula, where it's just n choose r. Okay, so if you were to have like a binomial term like a plus b, if you raise it to the power of n, we're going to get n plus 1 terms, right? So the first term we're going to get is n choose 0, And then we're going to get a to the power of n, then b to the power of 0. Then we're going to get n choose 1, a to the power of n minus 1, b to the power of 1. And this pattern continues until we get, say, n choose n, a to the power of 0, b to the power of n, right? So this is succinctly written as r goes from 0 to n, and n choose r, a to the power of n minus r, b to the power of r. So you just need to use this template to interpret these two statements. Right? Then we'll be able to solve for a and b. So 448 is the coefficient of x to the power of 6. So we get 448 x to the power of 6 as a result of one of the possible values of r. Right? So since the n is 8, we would have 8 choose r times ax cubed to the power of 8 minus r times b to the power of r. Right, so we should choose the right value of r in order to get x to the power of 6, and then we can work out what the coefficient's going to be. 2880 x to the power of 6 is found by 10 choose r, ax cubed to the power of 10 minus r times b to the power of r. Right? So we can solve for these two pieces of information and see what we get. So I'm just going to write this here. So if we end up doing that, we get 8 choose r times... Okay, so actually we can just work this out in our head first. Or actually, let me just write it down. So we have a to the power of 8 minus r, b to the power of r, and then we get x to the power of 24 minus 3r. That's going to equal 448 x to the power of 6. Then 2880 x to the power of 6 is going to be 10 choose r, a to the power of 10 minus r, x to the power, we'll write b to the power of r, and then x to the power of 30 minus 3r. So for each of these, we want to look for when r 24 minus 3r is 6, right? That would be when r is going to be 6. Right, so for the first one, we want to put in 6 where the r's are. And then for the second part, we want to have 30 minus 3r is going to be 6. So in this case, r should be, so if you have 30 minus 3r, so we would get 30 minus 3r, that's going to be 8, right? So r is going to be 8 here. So we can just plug that in. Okay. So that means 448 is the result of a to the power of, so I'm going to write here. So 448 is the result of a to the power of 8 minus 6, or we'll just say that's like a squared, b to the power of 6, and then x to the power of 6, and 8 choose 6, right? Next, we have 2880. That's the result of plugging r equals 8 here. So we'd have a to the power of 2, a squared, b to the power of 8, and then we'd have 10 choose 8. Okay. So if we solve for these, we should be able to get our a and b values. But let me just check what the combination values are. So if you have 8 choose 3, or if you have 8 choose 6, that's going to be 28. So 28 a squared b6 is 448. And then 10 choose 8, what's that going to be? That's going to be 45. So 45 a squared b to the power of 8 is 2880. So we could go for like dividing the equations, right? So if we divide 45 a squared b over 8 by 28 a squared b to the power of 6, we're going to get like b squared left. Okay, so to summarize this, we're going to get b squared is going to be 2880 divided by 448, but then we want to multiply like the 45. We want to divide the 45. And we want to multiply the 28. Right? So this ends up giving us b equals 4. Or b squared is going to equal 4. So b is going to be 2. And a, since it's positive, is going to be, let's do like 448 divided by 28. And then we want to divide by b to the power of 6. So we want to divide by 2 to the power of 6. So a squared is going to be 1 over 4. So a would have to be 1 over 2. Okay, so if you solve for all of that, it should give you a is 1/2, b is 2. So you can kind of like choose your own method of solving for these, or when you're going to bring in your calculator, but it all starts from these two relationships. Okay, so using the binomial theorem, we set up an equation that equals 448 x to the power of 6 and 2880 x to the power of 6. And you can figure out, based on the number of degrees of x, what's your value of r. Then you can substitute that value of r in to work out the values of a and b. Okay. So you just need to plug and play your formula booklet and you should be good to go. Let's move on to number 6. We have complex numbers. And with complex numbers, you need to be both familiar with the Cartesian form, like z is a plus bi, but you also need to be familiar with the cis form, or the polar modulus argument form, like r times cis theta. And with modulus argument form, we have the de Moivre's theorem, right? So if you have z to the power of n, we basically just multiply the modulus by n times. And the argument is multiplied by n. So we have cis n theta. Okay. So this is something to keep in mind when you do these complex number problems. So let's begin. So we have z to the power of n is negative I. So we would say like z to the power of n, that's just cis. So if z is going to be cis 11 pi over 18, then z to the power of n is going to be cis 11n pi over 18. And we're asking ourselves, like, what positive integer value of n should we have in order to have negative I, right? So let's try to write out what I would be, or negative I would be. So negative I would be like here. So in terms of this argument, we want like pi over 2. So if you have cis pi over 2, note that this will give us cosine of pi over 2 plus I sine pi over 2. Right? Or actually, if you want, my bad. So if you want negative I on the argand diagram, you actually want to draw it like this. So this is the real axis. This is the imaginary axis. So you want to draw this one as negative I. So we want to go like 3 pi over 2, or 270 degrees. Okay. So we want to look for the argument of 3 pi over 2. Right? So negative I is going to be cis of 3 pi over 2. But we don't have to stop there. It could be this plus any multiple of 2 pi, right? So we could have cis of 3 pi over 2 plus 2 pi k. That's going to be our negative I. So what we're looking for here is we want our 11n pi over 18. This is the argument. This should equal 3 pi over 2 plus 2 pi k. So you can try working it out on your own, but my guess is you want to go for when k is going to be 0, right? If k is 0, then we have the smallest possible value, and we'll try to make 11n pi over 18 equal to 3 pi over 2. If it doesn't work, we'll try higher values of k. So if you have 11n pi over 18, let's say it's going to be 3 pi over 2. Then that gives us the idea that n is going to be 18 times 3 over 22. So that's going to be, n has to be like 27 over 11. Okay, but we want n to be a positive integer, so obviously that doesn't really work. So what we could do is we could look for some higher values of n, right? So what if we have, okay, so k equals 0 doesn't work. So what we could try is, if you want our argument to be a multiple of like pi over 2, then we would have to try doing like n equals 9. Right? So if n equals 9, then we would get 11 pi over 2, which works because we'd have 3 pi over 2 plus 4 pi. Right? So we could say that k could be 4, and if k is 4, then n would be 9. So the smallest value of n would then be 9. Okay. Now for b, how could we get z to the power of 10 from z? So z to the power of 10 will be cis 110 pi over 18, right? If we try simplifying that, it would be 55 pi over 9. And if you take out a bunch of 2 pi's, right, we know we can take out at least like 54 pi here, because 54 pi over 9, that's going to be 6 pi. So we know it's like a periodic thing. We can just take out that. So z to the power of 10 is equivalent to pi over 9. So how do we go from z, which was 11 pi over 18, to pi over 9? So what we could do is that our value of z, so the modulus is all going to be 1, right? So z was somewhere around here because the argument is 11 pi over 18. But what we want to end up is here, right? So we get pi over 9. So we want to go back by 11 pi over 18 minus pi over 9. Or that would be like half pi. So in describing the single geometric transformation, you could say rotate z by negative pi over 2 radians. Right? So we can do rotate by negative pi over 2. Right? Or you might say rotate by positive 3 pi over 2. Okay? So both would work. All right, now on to number 7. We have a tree diagram where we have to visualize like the different probabilities of different events. So let's just work on using the fact that complementary events sum up to a probability of 1. Right? So there's a test where we're testing for the presence of a gene. So if there is a gene, we have G, otherwise you have G prime. So this would have a probability of 1 minus P. Right? If P is a proportion of parrots with this gene. And then we have a false positive result and correct positive result. So a correct positive would mean that the parrot has the gene and we correctly tested to have that. So the other 5% of the times, right? So 95% of the times we're correct in getting the positive result. Other times we get a negative when we should have gotten a positive. Meanwhile, the positive false result. So the false positive means there is no gene, but we think there is, right? So that's 2%. So the true negative would be 98%. Okay, so this would be the tree diagram. And I guess this would come in handy for the next problem, because we have a conditional case. So there's 100 test results that returned positive, right? And we want to find what P is based on the testing, like the test results, right? So we want to see the big picture, because what we're saying is the probability of the parrot having the gene given that we got a positive result is 132 over 150. And the probability of the parrot not having the gene, even though it got a positive result, is 18 over 150. So it's kind of confusing, because usually we kind of said that given that the parrot has a gene or doesn't have a gene, like that's the initial condition, and then we go for the results, is it positive or negative? But in this case, we're flipping that, right? So given that we got the result, right, what's the chance that it has a gene or doesn't? So let me just redraw the tree diagram from earlier. So the parrot could have the gene or not have the gene, and then it could get positive results or negative results. So what happened is, just assume this is what happened, right? We got a positive result, and the parrot either has the gene and got a correct positive, or it doesn't have the gene and we got a, incorrect, like a false positive. So this is 150 parrots, and this was 132, this was 18, right? So this is what it's looking like, and we're looking for P. So we're saying that this is P, 1 minus P, this is 0.95, and this is 0.02. The total number of parrots would be 0.95 times P plus 0.02 times 1 minus P, right? So this would be the total number of parrots who got a positive result regardless of where they actually had the gene or not. But then the parrots that correctly got the result would be like the P parrots times 0.95. So that would be equal to 132 over 150, and we just got to solve this equation to find P. Right? So I would get 0.95 P, this would give me 0.97 P, or 0.93 P, plus 0.02 is 132 over 150. Okay. So I could just do 0.95 times 150. So on the left, I would get 147.5 P. Or actually, if you do it to decimals, it's 142.5 P. That is going to equal 132 times 0.93. So that's like 122.76 P plus 132 times 0.02. That's like 66 over 25. So that's like 2.64. So we have 142.5 minus 122.76. So if you do 2.64 divided by this number, that should give you the correct value of P, which is 0.1337, or P is roughly 0.134. Right, so we can correctly predict the actual proportion of parrots that have the gene. Okay, so this relies on your knowledge of conditional probability, and there's a Bayesian formula for relating these given condition events. Okay. Next, let's move on to number 8. So we have a vector and plane problem. So you have access to all the formulas, but I would strongly suggest you try to develop an intuitive understanding of what this is, right? Because then it'll be clear like what kind of calculations you'd have to perform. So what I mean by that is, let's say we have the angle between a line and a plane, right? So you want to draw like a situation where we have the plane, and you would say there's a line, right? So if you have a line that goes through like this, the angle is given to be alpha, right? So I mean, if you just draw a line like that, you would just end it saying this is alpha. But with a proper understanding of vectors, you know what's important is that we have a normal vector, n, right? So oftentimes, instead of trying to find the angle between like the plane, a line on this plane, and the actual line here, it's often more beneficial to try finding the angle between the normal vector and this line. So this would be like 90 minus alpha, right? So let's try to find the direction vector of this line first. So if you say this line has a direction vector of d and the plane has a normal vector of n, then what we're going for is the dot product formula, because if you have n dot product d, that's going to be equal to the modulus of n times modulus of d times cosine of alpha, right? But in this case, it wouldn't be alpha, it would actually be pi over 2 minus alpha. So this is the important part. Like your textbooks or formula booklets, they're not going to tell you whether you should be using like alpha or pi over 2 minus alpha, but upon drawing this diagram, we know that this angle is 90 degrees minus alpha. Right? So we are still solving for alpha, but the relationship is based on this angle, not the actual angle here. Okay, so the normal vector for this plane is going to be 4 cosine alpha and sine alpha, right? Dot product with the line vector. So the line vector, we can try finding that by setting all of this equal to t, right? A single parameter. So x would be 3t plus 1, y would be 2t minus 2, z would be negative t plus 5, right? So the direction vector of this line will then be 3, 2, minus 1. So now we're just going to plug this all in. So we'd have 4 cosine alpha, sine alpha, that direction, dot product with 3, 2, negative 1 equals square root of this modulus. So we get 4 squared plus cosine squared alpha plus sine squared alpha times square root of 3 squared plus 2 squared plus negative 1 squared times, we have cosine of pi over 2 minus alpha. But this is a shortcut. We know that cosine of pi over 2 minus alpha is the same as sine of alpha, right? Because if you have complementary angles, right, the cosine and sine relationships are the same, right? Because they both add up to 90 degrees. So this is what we're going to solve, and eventually we should be able to solve for what alpha is. Okay. So one line below that. So performing this dot product, we just multiply the components. So we get 4 times 3, so it's going to be 12 plus 2 cosine alpha minus sine alpha on the left. On the right, we get 16 plus cosine squared plus sine squared, and by trig identities, we know that's going to be 1. So it's just going to be root 17. And then we get root 13 and 14, right? 9 plus 4 plus 1, that's 14. And then we get sine alpha. Okay, and you could do a bit more algebraic manipulation here, but I think this is good to go. You could just go enter this into your calculator right away to use your graph, right? So on the left side, you might have 12 plus 2 times cosine alpha, or cosine x, minus sine x. On the right, we would have square root of 17 times 14. I'm going to write this as 1. This times sine of x, right? So these two should be intersecting, and alpha is between 0 and pi over 2, so I just want to make sure that I'm looking in the correct place. So, I mean, alpha would not be greater than 2, right? Because pi over 2 is like 1.5. I'm working with radians. If I look for the graph, 12 plus 2 minus sine x, and then I have this times sine x. Right, so I should be able to look for the intersection. Right bound, I'm going to say is like pi over 2. So my intersection happens at 0.93239, or alpha is going to be 0.932. Right? So this is the value of the angle between this line and the plane. Okay. So I would strongly recommend that you solve a lot of these vector application problems, because there's a lot of places where you could be thrown off, right? You might use alpha instead of pi over 2 minus alpha, or you might use a cross product instead of the dot product. So yeah, you need more familiarity with these topics, so I would suggest you do a lot of these practice problems. Okay, now we have a proof by contradiction problem. So along with induction, this is one of the most common cases for proofs in the IB. So let's look at the statement. If you have p squared minus 8q minus 11 that should not be equal to 0 for any P and Q. So in order to prove that by contradiction, we want to say the exact opposite. We want to assume P squared minus 8Q minus 11 is 0. And then upon some manipulations, we'll show that that can't be true. It's going to be false, right? So let's just assume the true proposition. So let's just assume that P squared minus 8Q is 11. I mean, or we could just say like P squared minus 8Q minus 11 is 0. Or it's like saying P squared is 8Q plus 11, right? So we want to do something that involves like finding the left side and right side and showing that they're unequivocally, false. So the best thing to do is maybe like odd numbers. Right? So you want to see if these are even numbers or odd numbers, because if you look here, Q is a integer. So this is just saying like 2 times 4Q plus 5 plus 1. So if Q is an integer, 4Q plus 5, it could be an even or odd number. Actually, it's an odd number, but whatever this is also an integer. We're multiplying that by 2, so it's an even number, but we're adding by 1. So P squared is this, but we're saying P squared is a odd number, right? So that's the first finding we have. And we know that odd numbers times odd numbers, right? So odd times odd, that's going to give you an odd number. If you have an even times even, or even times odd, or vice versa, we know that that should give us evens, right? So if P squared is odd, we can then deduce that P is a odd number. Okay, so let's say since P is odd, we can write P is going to be 2K plus 1, where K is also a integer, right? So if that's true, we're going to see why the initial statement wouldn't really work. Okay? So just to kind of retrace our steps, 1, we would say if P squared minus 8Q minus 11 is indeed 0, then P squared is odd, right? 2, if P squared is odd, then we would say that P is odd, right? As well. Okay, so the statements we have is that if P squared minus 8Q minus 11 is 0, then P squared must be odd. Therefore, P is odd, but we're going to see this statement kind of break down. Okay, so let's try to show that P squared minus 8Q minus 11 is indeed 0. So we'd have 2K plus 1 squared minus 8Q minus 11. We're going to try and say that it's 0. So we want to contradict this statement. So if we expand this, we get 4K squared plus 4K plus 1 plus 1 minus 8Q minus 11 is 0. Let's move everything to the right. So we get 8Q plus 10 is equal to 4K squared plus 4K. Then we can divide by 2, so we get 2K squared plus 2K is equal to 4Q plus 5. Wait a minute, we just showed that K is an integer, so this is going to be an even number, right? And if Q is also an integer, then this is going to be an odd number, right? Because we have 2 times 2Q plus 2 plus 1, right? So we're going to have an even number plus 1. So this has to be false, right? There's no way we can find a K and a Q that satisfy this, right? Where one side is even, one side is odd. So the third statement, the last piece of the puzzle, would be that if P is odd, then P squared minus 8Q minus 11 cannot be 0, right? Because P squared is even in terms of K. So yeah, like if you have P squared minus 1, that was, yeah, so this statement, if we put in our K values, we just showed that this yields a statement where we have like an even is equal to an odd case. So we clearly show that if P is odd, right? So for P being equal to like 2K plus 1, where K is an integer, we just showed that this statement does not hold. Therefore, we just contradict the statement. it's like we initially assumed that p squared minus 8q minus 11 is equal to 0, but then that led us to these assumptions that eventually make this equivalent, this equality not hold. So yeah, like the steps 1, 2, 3, we're kind of going back to our argument and we're contradicting with our proofs, right? So this is proof by contradiction. So I think the key is to recognize that you can flip this equality to say p squared is 8q plus 11. That's like 1 point. And when you're trying to test for even and odd numbers, you can always do stuff like 2k plus 1 or 2 times k, right? That's like the standard way of expressing even and odd numbers. Okay, so that's how you would do number 9. Now let's do number 10. So we have a gutter that's in the shape of a rectangle with a sector area, right? So there's like a part of a sector area that's overlapping with a rectangle. And it says that the depth here is going to be 600. So if you have the cross-sectional area, we're going to get, cross-sectional area times 600 to get the volume. And what's interesting is that we get this by bending the sheet metal. So whatever this is, so it's like 10, 10, and then we have like the arc length. That should be equal to 45, right? And we have the angles here, so we can use a bit of triangle, circles formulas to do that. So I think the first part of this question will just be basic geometry, and then we're going to use calculus either for optimization or either for integration if you're trying to calculate like flow rates and like how long this is flowing. Okay. So we're probably going to be given like a flow rate and we're going to integrate over time. So that's how this question is going to go. You need to kind of keep track of your work properly because it's easy to make mistakes along the way. Okay. So let's say that theta is 2.08 radians. So that's the answer we're given. We want to show that is correct. Okay. So as we said earlier, if you have the arc length here, right, we have 10, and we have the arc length here. So we can say that L, the arc length, plus 10 is going to be 45. So L is going to be 25. Now, how do we find this L? Well, we could say this is theta, and we have our radius R, which was actually 12. Right. So this would just show 12 theta is going to be 25. So theta is going to be 25 over 12. So that's like 2.08. Right? It should give you, 2.08 radians. Okay, so that's how you would do part A. Let's now do part B. Find the cross-sectional area of this gutter. So recall from earlier that we have this rectangle where we have the width W, the height of this rectangle, which is 10, and then we have this circular part. So what we could do is we could add the rectangle, which would be like 10W, and then we could add this chord-like part here. But in order to do that, we would actually have to do add the sector area, and then we'd minus the triangle area. Right? So clearly, this is the entire sector, but we want to subtract the triangle area. That allows us to get the total area here, right? This shaded area. So if you do this, we want to find the sector area formula, which is 1/2 r squared theta. So 12 squared times 2.08 minus 1/2 12 squared times sine of 2.08. Okay, so now we have to find what the W is, and we can do that by using this triangle. Right, so remember that we have a triangle with two sides, 12, and the angle between is 2.08. So this is a SAS condition where we're using cosine rule. Okay. So if you have W squared, that's going to be 12 squared plus 12 squared minus 2 times 12 times 12 times cosine of 2.08. So let's find that out using the calculator. We have 144 plus 144 minus 2 times 144, because 12 squared is 144, right? 144 times cosine of 2.08. And then we want to square root that to get our W. So that's 20.69 or around 20.7. Okay. So if you put 10 times 20.7 plus this expression right here, we should get the combined area. So this times 10 plus 0.5 times 12 squared times 2.08 minus, we subtract the area of the triangle. So 0.5 times 12 squared times sine of 2.08. So if you do all that, it gives us 293.87, or we can round to 294 square centimeters. Okay, so that's how you would do part B. Now, we were faced with this integration problem because the rate of rainwater, right, that's going to be given as a function of time, right? So the rainwater is not entering at a constant pace. It depends on the time. I think it fluctuates depending on like how it's raining. So what we can do is you can say that if it's raining over a certain period of time, then the area underneath is going to be the total volume that has flown in, right? So if you want to find this from the first 60 seconds, right, we can find the area under this graph. That's going to give us the volume of all the water that's flown in, and then we can compare that against the actual volume, right? So what we want to compare is the volume that's flown in. It would be the interval from 0 to 60 seconds. And then we'd have the rate at which water came in, right? And then we would have this versus our volume. So remember we had a depth of 600 and the cross-sectional area was like 294. And that would be somewhere around 176,000, right? 3 cubic centimeters. So the comparison holds like this, right? So does this integral expression evaluate to a value that's greater than or less than 176,000? That's what we're going for. So you might have to do a bit of like integration by hand, but in this case we don't, because everything's given to you and this is a paper 2. So we can use our integration feature on our calculator. So we integrate from 0 to 60 and we have 50 cosine 2 pi t over 5 plus 3,000 dt. And let's see what that gives us. You go to your math, fn integrate. And then we have from 0 to 60, and then we get 50 times cosine of 2 pi divided by, or 2 pi times t divided by 5 plus 3,000. And 2 pi x. Oh, and you probably want to do this in radians. Oh, and if so you want to close the brackets here. Okay, there we go. And that gives us 180,000 cubic centimeters. So it does overflow because according to the function of rate of rainwater flowing, during the first 60 seconds, we have 180,000 cubic centimeters coming in, but the actual volume of the gutter that we found, which is 600 times cross-sectional area, that was 176,000. So by like a small margin, we would have the gutter kind of overflowing. Okay, so that's number 10. Let's go to number 11. So this is a probability density function. So usually we might have to normalize this by using the idea that the total area under the curve is like 1. But thankfully, in this case, we're not required to do that because we're just given the f of x right away. Instead, we just go for the exact value of expected value. So expected value of x is like multiplying x with your respective probabilities and sum it up. In the case of PDFs, we would just have integrate from 0 to 2 x times f of x, right? So f of x, it would just be 6 over this whole thing, right? So x times 6 over pi root 16 minus x squared dx. So we might just go to our calculator to find our integration, which I'll do for now. So if you put in from 0 to 2, and then we would get 6x divided by pi times square root of 16 minus x squared. I mean, sure, you could get an answer like this, but it's going to be like 1.023 something something, right? But the thing is, it wants an exact value. So the calculator is going to give you, as many decimals as it wants, but at the end of the day, it's only going to be a like rounded value. So the only way you can get an exact value in this case is to solve by hand, right? So basically, in the paper 2s, even though you're given a calculator, the way the examiners tell you that you have to use your manual integration skills is if they require a exact value. So let's try to integrate this manually. And I think we have an easy case for integration by substitution because we have a 16 minus x squared inside the square root. And if you differentiate that, we get like, negative 2x. So that has, that's going to cancel out the 6x at the top. So we're going to use substitution. So let me try that. So let's say we have u is 16 minus 2x squared. Then du is going to be negative 2x dx, right? So if we were to convert this, we would have, like, let's say we have integrate, and then instead of dx, we're going to write du. That means you have to have, like, negative 2x divided. So we had a 6x, but we're dividing by negative 2x. And then we're still writing our pi, and then we have square root of u instead of our 16 minus x squared. Okay. So that's how you would substitute out the x for u, right? And then one thing we have to do is we would have to convert the boundaries. So for definite integrals, right, we're integrating from x is 0 and 2, but we also want to integrate with respect to u, right? So u is 16 minus 2 squared, so that's going to be 12. And then we have u is 16 minus 0 squared, so that's going to be 16. So if you're integrating x from 0 to 2, we're integrating for u from 16 to 12. Right? So let me write that again. We would get negative 3 over pi. Right? Integrate from 12 to 16. And then we get u to the power of negative 1/2 du. So it's a bit awkward because the number at the top of the definite integral is smaller, but that's nothing more than just switching with a negative, right? So we just get negative area like this. So if this kind of is a bit unsettling, you can just write 3 over pi, and we integrate from 16 to 12, right? So we can reverse the order like that. So if we integrate this, we add 1, so the u to the power of negative 1/2 is now going to be u to the power of 1/2, and then we'd have a 2 in front, right? And then we would have, in definite integrals, putting this from 16 to 12, right? And then we'd have 3 over pi at the front. So if we put in 16 here, we would get 2 times 4, right? And 3 over pi comes here. And then minus 2 times square root of 12, which would be 2 root 3. So calculating all that, we would get 24 over pi minus 12 root 3 over pi. Okay, and if you check with our calculator, we would get So the value we were looking for is 1.023, but we would get 24 divided by pi minus 12 root 3 divided by pi. Yeah, so it does give us the same number, but we have more exact, like, radical notation. Okay, next, if you want to find probability that x is less than 0.5, we would integrate from 0 to 0.5 for this exact expression. And thankfully, we don't have to get the exact value. We can just use the calculator to find the approximate decimal value. So let's go over there, math, integrate from 0 to 0.5. And then we get 6 divided by pi square root 16 minus x squared dx. And that's going to give us 0.239. Okay. Next, let's move on to part C. So we have 2 milliliters of reagent, and we have independent trials that are identical. So we have a case of binomials, and we want to find the probability of success, having at least one success, right? And we want to make sure that we get at least like 99%. So what you do here is going to be the probability of at least one success. That's going to be equal to 1 minus probability of no success out of n trials. Right, so it's going to be 1 minus 0.239 to the power of n. And we want this one to be greater than 0.99, right? So if you just solve for n right away, you can just go straight to your calculator without further manipulating this. So we want the left side to be greater than the right. So we have 1 minus 0.239 to the power of x, and we want this to be greater than 0.99. So when does the intersection happen? So we want to be, so let's say that we're looking for larger values of n, maybe up to 20-ish. And the number is going to be from 0 to 1 anyway. So we do see an intersection from maybe like 0 to 20. That gives us 16.86. So n has to be greater than 16.86, right? That's when the blue graph is larger than the red. So that means the left-hand side is surpassing 0.99. So we need at least 17 trials for us to be at least 99% sure. Okay. Now let's go to part D. The probability that exactly 3 trials are successful. So as I've said earlier, this is a binomial distribution, right? So let x be, so if you let x be the number of trials, right? Or x is the number of reagent in milliliters, and we have like a trial that's considered a success. So let's say, let's call this like t. Okay, so let's say t is the number of successes out of like 10 trials, right? And this is either a success if x is less than 0.5, and it's a failure otherwise, right? If x is greater than 0.5. So t would follow a binomial distribution where there's 10 trials and the probability of success is 0.239. And we're going to count for how many successes we have. So the probability that t is going to be 3, that's just binom PDF, right? You just want to look for what happens when there's 10 trials with success probability of 0.239, and we want to see exactly 3 successes. So you can go to second variables, binomial distribution, PDF, and you get 10, 0.239, and 3. Right? So we get 0.242. And how can we have 3 successful trials consecutively? Well, let's have the F failures, right? The 7 failures are going to be here. And we have 8 spots in between. And the 3 consecutive trials can go in either one of these, right? Spots. So we have 8 ways. Because we have 8 places to choose from. These S's are going to move together. Next, we have the number of expressions. So if we have n trials, then how many ways can this happen? So it would be n minus 2 ways. Because we have n minus 3 Fs, right? So let's say we have a bunch of Fs, then we have n minus 2 spots, right, for the 3 S's. Then find the greatest value of n such that the probability of 3 consecutive trials is more than 0.05. So the number of ways in which we get successful 3 consecutive trials is n minus 2. We want to do that over maybe n choose 3, right? So the greatest value of n such that we get... Okay, so it's given that 3 successes have already occurred. So the total number of ways in which we can get 3 successful trials is this one, right? And then this would be the consecutive trials. So we want this to be greater than 0.05. Right, so this is just any 3 will be successful. This will be 3 consecutive successes. So this proportion has to be greater than 0.05. So we'd have n minus 2 over. This one would be n times n minus 1 times n minus 2 over 6, right? Because we'd have n factorial, n minus 3 factorial, or n factorial over n minus 3 factorial times 3 factorial. So simplifying that, this is what we get. This would then be 6 over n times n minus 1. And we want this to be greater than 0.05, right? So if we solve for this condition, we should be able to find how many trials we would need. So you get 0.05, and then we get 6 divided by x times x minus 1. So the intersection would go as follows, maybe 16. So we would need around 11.46. So n would be less than 11.46, so the greatest value of n. So for this to be true, according to our calculator, we have n has to be less than 11.47-ish, so 11 trials is the greatest number that we could get. Okay. All right, so let's now do the final question. This is a bit challenging because it is differential equations, Euler series, Maclaurin series, all packaged into one. Not only do you have to use your formula booklet and your working knowledge of analytical methods, but it's also a place where using the calculator to your advantage is really important, especially for Euler series. So you want to watch closely for how I would use, I would recommend that you watch closely for like calculator shortcuts or some useful features, okay? So we're given a dy over dx expression, and we're told that when x is 0, y is 3. So we want to solely crawl towards x equals 0.15, right? So what we're saying is this formula tells us the instantaneous slope at any point, right? So it's going to let us find our instantaneous rate of change. And what we're going to do is we're going to start from x equals 0, but we're going to slowly creep towards 0.15 in minuscule steps. And we're going to go like slope by slope, and we're going to find our value of dy over dx. So without actually solving this differential equation, we're just going to approximate it, right? So the key thing to realize here is that we're going to update our values of x plus h into our x. And we're going to say y is going to be the step size plus, times the slope, right? So this would give us a new value of y, and we would repeat this. Okay. So this is what Euler's method wants you to do, and you could kind of work this out by hand, but since there's going to be 5 steps, and we need 6 sig figs, might as well use our calculator. So my setup would usually go like this. We have our trials of n, and we have our x and y values. So for trial 0, right, our starting point, I would say that we have x is 0, y is 3. And if you were doing this by hand, you would calculate your dy over dx value. Right? So for instance, if we calculate our dy over dx value, we get 0 squared times 3 minus 3 all over 1. So this would be negative 3 actually. So what that means is we start at like 0, 3, and the rate of change is going like negative 3. So if you were to go 1 in the x direction, your y value would go down by 3, right? But of course the slope is going to change, so we're going to pretend we only move like a step size of 0.03. So in one step, we move by 0.03, and we would do like 3 plus the slope times the step size, right? So step size times the slope, that's going to give us how much change in the y we got. So we're going to get like 2.91, and then we'd have to calculate the new dy over dx value again, and we have to do that for 5 steps. But it's going to get messy because there's a lot of rounding and decimals, right? So let's use the store feature on our calculator to do that easily, right? So once you get the hang of this, you'll be able to knock out these Euler's method problems in no time. So depends on the calculator, but I see like the store variable button on my TI. So this basically allows you to store numbers into your value variables. So I would say like 0 store x. So whenever I write x, it's going to know that I'm meaning a 0. So if I write 2x plus 1, right, that means I have 2 times 0 plus 1, so it's going to be a 1, right? And then I can store the value of 3 into my y. So I'm going to write, say, y right here. So whenever I write a y, I'm going to get 3. Okay, so if I have like x times y, that's going to give me a 0 because it's 0 times 3, right? So, so we can always like update our stored variables, stored values. But what I'm going to do is I'm going to use a definition of x. So I'm going to use x in the definition of x, right? So I'm going to use like this recursive definition. So I'm going to say I'm going to update the value of x, right, by adding the previous or the current value of x and adding a certain number to it, right? But first, let me update my y. So I'm going to update my y by taking the current value of y, and I'm going to add to it the step size times the dy over dx. So the current value of the slope is going to be like x squared y times y minus y divided by x squared plus 1. So x squared plus 1. Yeah, so x squared times y minus y all over x squared plus 1. That's going to be my current slope value, which I already found to be negative 3. And I'm going to say negative 3 times 0.03 plus y. That's going to be my new y value. Okay. So I just updated my y to be 2.91. And then I'm going to update my x value by adding 0.03. Right? So this x plus 0.03 is going to replace the previous value of x. So yeah, I have 0.03 and 2.91. Now, I just need to enter this function like 4 or 5 more times, right? So without like repeating anything. So if I do this one more, I get 0.064x, and I get 2.822857-ish for y. And I can do that like 3 more times. Right, so now I get the value when x is 0.09. I want to update my y value once more and x value once more. And then I'm going to update my y found time. Right? And I guess I don't have to update my x, but it would be 0.15. So the n value I get is 2.580462, right? And that is how you would get your answer correct to 6 sig figs. Even if you did it manually, like the tricky part is you would have to write out all the decimal places. Otherwise, if you round in between or round prematurely, you wouldn't get this exact value. So I would strongly recommend that you use this store variables method to get Euler's method done. Okay. Next, let's go on to number 2, part B. So what is the value of dy over dx when x is 0? Well, we kind of already did that. It's -3, right? Because we had x squared y minus y over x squared plus 1, right? So we just basically put in x is 0, y is 3, and we plugged it in here. Next, show that d squared y over dx squared. So the second order differential is going to be 3 when x equals 0, okay? So let's just remind ourselves, y is 3 and dy over dx is -3 when x equals 0. So we're going to find the second order differential. So we could do that by differentiating dy over dx one more time. So that would be x squared y minus y over x squared plus 1. Okay. Yeah, so instead of using your calculator, you would have to do this by hand. All right, so what I'm going to do by hand now is I'm going to differentiate the expression for dy over dx once more. So I get like the second order differential. So I'm going to differentiate this rational expression like x squared y minus y all over x squared plus 1. So basically, it's going to be the quotient rule, right? It's like if you're trying to differentiate u over v, it's going to be u prime v minus uv prime all over v squared. So I'm going to do exactly that. So I'm going to get x squared y minus y prime times x squared plus 1 minus x squared y minus y times x squared plus 1 prime all over x squared plus 1 squared. Okay. That is what d squared y over dx squared is going to be. Okay. So d squared y over dx squared is now going to be, if you differentiate the first one right here, we would get 2xy minus, or 2xy plus x squared times dy over dx because of the product rule. Then we get minus dy over dx, right? So when we're differentiating x, no problem. When we're differentiating y, we want to have implicit differentiation. So we want to multiply out a dy over dx. Then we get x squared plus 1 as usual, minus x squared y minus y, and x squared plus 1 differentiated, that's just 2x. This goes all over, right? Single denominator, x squared plus 1 squared. Now we want to substitute in our values like x is 0, y is 3, dy over dx is -3. And thankfully, the denominator is just going to be 1, right? 0 plus 1 squared. So the d squared y over dx squared is going to be us just substituting in these values for y and dy over dx. But before doing all of that, we can just cancel out any terms that have a 0, right? So if you have 2x, I mean x is 0, so this term just goes away, right? Because we're multiplying 2x to whatever this is, all of this goes away. And we would eventually just get, if you were to substitute, so this one would be a 1. These terms will all go away, and then we get negative dy over dx. So negative dy over dx over times 1 over 1. So that's just going to be 3. Okay, so using quotient rule, you do a bit of like algebraic calculations and simplify and substitute. And at the end of the day, it's more simpler than it looks because the end result is just going to be 3. You're going to have a lot of terms that just cancel out because there's like a multiplication of 0 in here, right? Or, yeah, 1 in here. The denominator is 1. So it's going to be pretty simple. It all cancels out and gives you a neat 3. Next up, we have part C. Given that the third order differentiation, like d cubed y over dx cubed is 9, let's find the first 4 terms of the Maclaurin series. So if you go to your formula booklet, the Maclaurin series is f0, f prime 0, x plus, and technically there is the factorials that you have to write. F double prime 0, x squared over 2 factorial, plus f triple prime 0, x cubed over 3 factorial, plus, if they want the first 4 terms, that's all we have to do. So you could keep on going, but with like the fourth derivative and x to the power 4, but yeah, this is all you need. And earlier we found out that when x is 0, y is 3, so we get 3. Right, and by the way, 0 factorial and 1 factorial, they are both 1, right? So for your reference, this is 1, this is 1. We had x is 0, y is 3, dy over dx is negative 3, and d squared y over dx squared was 3 from earlier. So we get 3 minus 3x plus 3 over 2x squared plus 9 over, so it's set to be 9, so 9 over 3 factorial x cubed. So that would be the first 4 terms. Let's just simplify once more. 3 minus 3x plus 3 over 2x squared, and then you get 9 over 6, or 3 over 2 x to the power of cubed. Okay. And if you were to use this approximation, so we don't know what the formula for y in terms of x is because we haven't solved it yet, but we can put it into this Maclaurin series to approximate. So we'd have 3 minus 3 times 0.15 plus 3 over 2 times 0.15 squared plus 3 over 2 0.15 cubed. Let's see what that gives us. 3 minus 3 times 0.15 plus 1.5 times 0.15 squared plus 1.5 times 0.15 cubed. So if we convert that to decimals, that's going to be 2.588125. And we want 6 sig figs, so 2.58881 would be the 6 significant figures we're going for. Okay, so that's another way. The first method was Euler's method, the second method was Maclaurin series, and we'll have the third method of solving this, which is actually solving this differential equation ourselves, right? So we want to get the y equals f of x form, and then we will substitute in like our x value, because that's going to give us the most accurate value, right? Our analytical solution, right? But the reason we can't do this all the time is because if the expression becomes a bit difficult, sometimes it's impossible to solve the differential equation. So that's why we resort to other methods like Euler's method or Maclaurin, because that's good enough. But anyways, let's get to it. So we can say that x squared minus 1 over x squared plus 1, that's equivalent to 1 minus 2 over x squared plus 1. Okay, so let's see how that comes in. So we want to solve this by separation of variables, right? So if you have dy over dx, that's y times, we can group out the y, common factor. That's x squared minus 1 over x squared plus 1, right? So we kind of see that this is given to us as a hint. Then we get dy over y is equal to x squared minus 1 over x squared plus 1 dx, right? And we can always integrate both sides. So if you do that, we would get ln y plus c1, some constant, and then we would get integrate, so we would basically integrate like 1 minus 2 over x squared plus 1 dx, right? So we know that just becomes an x here, and this is arctangent, right? So if you go to your formula booklets, if you differentiate arctangent x, that's going to give you 1 plus x squared. So this is going to be negative 2 arctangent x. Right? And then we would have a new constant here. But instead of writing it like this, we could simply merge the constants together. right? So instead of writing an integration constant on both sides, we can just write this as a single thing. So we could just write this as so we could just write this as ln y is x minus 2 arc tangent x plus c. Okay. Now, recall from earlier that when x is 0, y was 3, right? So you'd have ln 3 is negative 2 arc tangent 0, right, plus c. But arc tangent 0 is just 0, so that would just be c. So actually, using our substitution, we would say c is ln 3. So, if we were to write the equation again, we'd have ln y is equal to x minus 2 arc tangent x plus ln 3, right? And we're trying to find the function for y. So if you want to do that, we could do, we could subtract ln 3 on both sides. So we get ln y minus ln 3, or we could kind of simplify that into ln y over 3, right? So we could say ln of y over 3 is equal to x minus 2 arc tangent x. And then one final simplification would give us y over 3 is equal to e to the power of x minus 2 arc tangent x, right? And y would therefore be 3 times e to the power of x minus 2 arc tangent x. Okay, simple as that. So D part 1 would be us performing the separation of variables with the hint given, right? And using our knowledge of the formula booklet, right? Integral for arctangents and whatnot. So if you got this expression, we can now easily get our final points for 2. So it says find the value of y when x is 0.15. So we just want to substitute in 0.15 here. So we get 3 times e to the power of 0.15 minus 2 arc tangent 0.15. Yeah, so where the x's were, we now put in the y. So making sure that we're in radians, we'd have 3 times e to the power of 0.15 minus 2 times arc tangent times 0.15. Okay. So that gives us 2.58786 up to 6 significant figures. So where does that bring us to the final conclusion, right? So if you're comparing the results we got from Euler's method, which is 2.58046, and if you get the value from the actual analytical method, so I guess it would be the actual. So this would be the approximate value. This would be the actual analytical value, which we solved. It was 2.58786. So clearly the actual value is bigger, and the Euler's method is underestimating that. So what's the reason for that, right? Why will this always be underestimating? Well, earlier on, we found that d squared y over dx squared was 3, right? And this was, of course, when x is 0. So I guess we don't know what the graph will do later on as x gets really large, but if x is between 0 and 1, for the time being, we know that our graph is concave up, right? So if this is x and this is y, we started off at 0, 3. And we actually took a few incremental steps towards 0.15. And what happened was we actually got, so if it's concave up, the graph is going to do something like that, which is why the actual thing is 0.15, 2.58786. But what we did with Euler's method is we found the slope, right? Or actually, we start from 3 and we have to go down, actually. So let me just rescale that. So we still have a concave up graph, but we would have to go down a bit. So, oops. So it's only worth 2 points, and on the actual test, like, okay, so what you have to write is, since d squared y over dx squared is greater than 0, we would say it's a concave up graph. Therefore, Euler's always underestimates, right? I mean, that's pretty much what you have to write, but to give you an actual, like, in-depth explanation of what's going on, this is what you need. So we start off with x equals 0 and y equals 3, right? And we had our, so if it's concave up, this is what's going to happen. Right? So this is so what's going to happen is that dy over dx is negative, but becoming less negative as we go on, right? So we're going to have like a steep dive at the first part. So when we found like dy over dx at the beginning, right, the slope was like -3. So we assume that we kind of go by 0.03, and we had our value of y here. So this would be clearly lower than that, because the actual slope is becoming less negative, but we're assuming it holds true. Then we calculated the new slope here, and then we went by 0.03. But again, the actual slope is changing in real time. So we're going to kind of like curve our descent as you go. But Euler's method kind of has to take that steep, rigid drops, right? So the d squared y over dx squared, that's positive. So our slope is going to increase continuously. But Euler's method doesn't really account for that. Therefore, we're constantly underestimating our value of y. So if you want Euler's method to have a better performance that better approximates the actual thing, you want to decrease your step size, right? So ideally, you want to make sure that the step size goes to 0. You want to decrease step size. Then you'd have a method that's as good as the actual analytical thing. But the trade-off is that means you have to do as many calculations and steps. So yeah, you can basically take more time and computational resources to get a more accurate calculation, or you could just take a solution that's good enough, right? So that's how you would do the last section. And yeah, like usually the last questions are reserved for differential equations, but with enough practice, nothing's impossible. So thank you for watching. I'll catch you next time.